Hey, Miss Holly.
Oh,
Hello.
sorry, I was on mute. Yes, go ahead, Vance.
So I had a question.
Sure.
Um, Hold on a minute, let me find it. Oh, so can you explain like what's polar again and how to find like on the study guide? It's question number 17.
Okay.
Like polar, and I couldn't really find the answer for that one.
Yeah. Okay. So if you look at your book, there's a chart. Let me see what page it's on. I think it's in chapter 8, like 8.5. Let me see. Yeah, it's on page 265.
All right, I see.
And so you're going to use those numbers. And for example, for the first one, it says C to O. And so you look up C's, which is 250, 2.55,
Yep.
O's, 3.44. And you just subtract the two. It doesn't matter which way you go, whether it's positive or negative, but you find
Okay.
the difference between the two. And
Uh-huh.
that would tell you its polar character.
Okay.
And then the higher the number, the more polar it is.
All right, I see. And then also for number 16, how do I find or how do I figure out if the molecules from question 15 are polar?
Okay.
Um,
So for that one, you'd want to draw out the Lewis structures. For example, if you are looking at, for C, you have this. Well, the S's are going to pull electrons to themselves. You know, atoms want to pull electrons to their nucleus. So each S will pull electrons to themselves, but they're equal and opposite pulls. These are the same atoms. They're the same strength. So
I
they
see.
pull. And so that would make it balanced. And if it's balanced, it's nonpolar.
Okay, so like A, would A be polar because there's a balanced electron pair?
Yeah, exactly. You know, so for that one, you know, you do have an F pulling this way, an F pulling down that way, and an F pulling this way. But like you said, you don't have another one pulling up, you know, so this lone pair up here doesn't pull electrons. And so because there's no upward pull, it's not balanced.
I see.
So this would
Okay. Yeah.
So because we know it's, so if it's not balanced, we know it's polar.
Okay, I see now. And then I have one final question for number 20. What are sigma and pi bonds?
So there are just two different kinds of bonds. In a sigma bond, they orbitals overlap. So if you were to look at the electron orbital, let me see which one we're looking at here. So for HI, so H has one electron, then you have I, I'll use a different color for that one. So iodine has 7 electrons. And then hydrogen has 1 electron. Well, when they bond together, they're going to share electrons. So the ones that are shared would be this purple and blue one. So actually, you know what? I should show that that one's being shared by doing this. No. So these are shared right here.
I see.
And that's a sigma bond when you have an overlapping orbital. So this would be sigma when these two orbitals, in the circle is the orbital. So this is an orbital with a circle around it. And then when they overlap, that's a sigma bond. A pi bond is more complicated. And that's where the p orbitals are next to each other. You will not see that in a single bond. You know, so for this one, HI is just single. So if it's just a single bond, that's always a sigma bond.
All right.
You would need to have a double or triple bond to see a pi bond.
Okay, I see.
So if you're looking at, what else do we have on there? Oxygen, for example, when you have two O's bound together. Let me draw that out. So for O2, you have 6 electrons around each one. Okay. So they're going to share their electrons like we showed up here first in a sigma bond. So this would be a sigma bond right here because they're overlapping orbitals. But you also would have electrons in a p orbital. And so you'd have this, remember what p orbitals look like? They're kind of like, you know, these dumbbell shapes, like this. And so what would happen there is these 2 extra electrons right here, you have one right here and one right here, they would be actually shared within this p orbital. And so the p orbitals don't actually overlap the same way that the sigma ones do, but what you'd have would be 2 p orbitals that share electrons, but they're not overlapping like in sigma.
Okay.
And that's
So
called a pi bond.
all right. So when it asks how many sigma and pi bonds do each contain, I would say like for O2 there's 1 sigma and 2 pi.
Actually, even though it looks like 2, this whole thing would be called 1 pi bond. And it's a little bit confusing, but 1 pi bond looks like all of this.
All right, I see. Okay.
If you had 2 pi bonds, then you'd have another p orbital coming off this way, like that, and like that, where you'd actually would have these overlapping too. I can't really draw it on here, but you would have an overlapping of 6, actually, I'm sorry, 8 total lobes if you had 2 pi bonds.
Oh, okay, I see.
I don't think your book has a picture. This would be easier if you could see it in your book, but I don't think they show you what that looks like. No, I'm not seeing it. So just know that you have, for 1 pi bond, you have an overlapping of 4 total lobes of a p orbital.
And then what chapter is that on? I couldn't find it.
It should be, it's in chapter 8. Let me see what section it's in. Oh, here we go. It's on page 246.
Ah, found it. Okay.
Yeah, it kind of shows you, I mean, it's not the best picture, but it kind of shows you what it looks like.
Yeah.
So the only thing you have to know, you don't have to look like, you just need to know how many there are in each bond. And so just know that in a single bond, it's always 1 sigma. In a double bond, it's always 1 sigma and pi. In triple, it's 1 sigma and 2 pi. And that's all you have to know.
Wait a minute. So, wait, can you repeat that?
Yeah. So in a single bond, it's always 1 sigma. In a double bond, you always have 1 sigma and 1 pi. And in a triple bond, you always have 1 sigma and 2 pi bonds.
Ah, I see.
And so that's how you know. So it's just based on how many bonds you have.
Okay, I see now. All right, I think that's it for today.
Okay.
But I'll probably have more questions tomorrow.
Sounds good.
Okay, thank you.
You're welcome.
Miss Holly,
Yes, Robert.
I had a question on number 26.
Okay. So 26. Is there a certain one or is it all of them?
Yeah, kind of all of them.
Okay. So for that one, you would need to look on the activity series. You see where that is in your book. Forget. I forget what chapter this is in, actually. Let's see. Do you remember what chapter this section is? I'm blanking on that one.
No, ma'am.
Let's see. Because there's a chart in your book that you need to use. It's called the middle activities chart. It's probably in chapter 9. Okay, yeah, it's on page 293. So on page 293, you're going to find, it's going to tell you which metals are active. And the one at the very top, lithium, is most active. And as you go down the row, they're less active metals. So what you need to do for, I'll just go through the first one with you. I can exit out of this really fast and get my cursor back. Clear this off. Okay, so for the first one, it says lithium is reacting, and that's solid lithium, reacting with potassium cyanide. And they're asking if a reaction would take place, and if it does, write out the products. So what has to happen here, this is single replacement, where the metal is going to kick out the other metal. So if this one is more active than the other metal, in this case, if lithium is more active than potassium, it will kick out potassium and take its place. And the reaction that takes place would be single replacement, in which you would have would be solid potassium, and then lithium would come in and make this lithium cyanide. Now, the way this would work is that lithium would have to be more active than potassium. You have to go to the chart to confirm if that's true. And what you would see is that is true. Lithium is above potassium. And so lithium can take the place of potassium. If it were reversed, though, if you had potassium out here and lithium in here, then you would have no reaction because potassium is less active than lithium. It can't kick out lithium to take its place. So you have to find the metal and the non-metal, and then determine, or actually, sorry, both metals, and determine which one is more active. If the one that's more active is on the outside, then it can take place.
And Miss Holly,
Yes.
would it always be a single replacement?
In these situations, yes. So if you're trying to predict what's going to happen, and you always have one metal on the outside, and then you have a compound, then it's always single replacement. The only question would be whether it's going to work or not. So, but besides that, every one of these for 26 are single replacement reactions, but some might not proceed. You have to determine if they can proceed or not.
Thank you.
You're welcome.
Ms. Holly,
Yes, Lydia?
on number 24, it says classify each of the reactions in question number 23. What do
Yes.
you mean by classify them?
Synthesis, combustion, single replacement, double replacement.
Oh, okay, that makes sense. Thank you.
You're welcome. Okay, so there's a question on 29. What was that? 29F? Check to make sure that that's, yeah, 29F, about how to convert it. So the first thing, I'll just go through all the steps just to make sure. So for the first part, you would need to take the grams of zinc and convert it to moles. So zinc's molar mass, 65.37 grams per mole. That will give you 5.2 times 10 to the negative fourth moles. And they're asking how many atoms. So we would now need to convert from moles to atoms using Avogadro's number. So for every 1 mole, you have 6.02 times 10 to the 23rd atoms. So multiplying that out, you would get 3.13 times 10 to the 20th zinc atoms.
Miss Holly,
Yes.
I also had a question on number 31.
Okay.
I'm just kind of confused with like the whole concept of how to do that.
Okay. I'll go through this. So for 31, you're given grams of Ca3P2O8. And they're asking how many grams of fertilizer can be made. So always the first thing you want to do if you're given grams is to go to moles right away and then convert to what you need to know. So we'll convert grams to moles. 150 grams of Ca3P2O8. Look up its molar mass, and you would get 310 grams in 1 mole. So we do 150 divided by 310, we get 0.4836 moles. Now the question is, how many grams of fertilizer can be made? And Ca3P2O8 is not fertilizer. We have to look on the reaction, and fertilizer is CaH4P2O8. We're at the equation down here. I'll just write out the parts that we need. So in this equation, we have one product, Ca3P2O8, which we know we have 0.4836 moles of. And we have two other reactants. We have H2SO4 and H2O, but we can ignore those for right now because we don't need those to answer the question. So I won't write those in, even though they are still there. It produces two things. One of the things it produces is CaH4P2O8, and that's the fertilizer. It also makes CaH4SO6, but we don't need to worry about that either. So we're asked how many grams of fertilizer are produced, and we're given grams of Ca3P2O8. And so those are the only two things we need to really look at in the reaction. And so I'll just ignore the other ones and look at just these ones. So if we're given moles of Ca3P2O8, we need moles of fertilizer. We look at the molar ratio between them. Look at the numbers in front. Now in this case, there's no numbers in front for either of them. And so it's a 1-to-1 ratio. So for every 1 mole of Ca3P2O8, you have 1 mole of fertilizer produced. So in this case, we know that there also will be 0.4836 moles of fertilizer produced. Now, if this were, say, a 2-to-1 ratio, we would have to double that number, but it's a 1-to-1 ratio. So we can just write in moles of fertilizer also being 0.4836. Now the question though is how many grams are produced? So now that we have moles of fertilizer, we can convert that to grams of fertilizer. So we find the molar mass of CaH4P2O8, and we get 234.1 grams. We multiply that, and we get 113.2 grams. And that's how many grams of fertilizer are produced. Okay, let me go through number, what was it, Lisa, 38. Let me go and clear my board. So it says you have 1 mole of gas at STP. So STP we know stands for a temperature of 273 Kelvin, a pressure of 1 atmosphere. And it says we have 1 mole of gas. So that's what N stands for in the ideal gas law equation. So we look at the equation that gives you these, PV equals nRT. and plug in the values that we know. So we know pressure is 1 atmosphere. Volume is the unknown. N is 1 mole. R is the gas constant. If you look it up in your book, you'll see that's 0.0821 liters times atmospheres over moles times Kelvin times the temperature 273. And you can just solve for volume at that point. So that would be the long way to go about it. Now there is a shortcut though. Avogadro's law states that 1 mole of gas occupies a volume of 22.4 liters at STP. So you actually wouldn't even have to do the calculation, you could. But if you memorize Avogadro's law, that's what his law says. And so either way would work for that one. If you go back to number 35D, Avogadro's law, that's what you'd put in for his law. 1 mole equals 22.4 liters at STP.
All right, thank you, Miss Holly.
You're welcome. Have a good day.
You too.